Hello everyone, my name is Fahad Ahmed and today I am presenting my project which is on converting food waste to fuel and testing the effect of temperature and enzyme dose on bioethanol production. But before we begin, I would just like to give you guys a small disclaimer that it is really hard to combine 6 weeks worth of data and efforts into one single page poster. So I would highly recommend you guys to visit the research paper to get more deep insights and analysis on how this project was done and what was there. So yeah, without any further ado, let's begin. So food waste is usually seen as something useless or something that just gets thrown away, often as a liability. But a lot of food waste, especially starch rich food waste, actually contains carbohydrates that can be converted into useful products like bioethanol. And since starch is easier to break down, and I wanted to look at whether a simple starch rich food waste could produce bioethanol under different fermentation condition. And the main question in this project was whether changing temperature and enzyme dose would affect ethanol production. And my hypothesis was that ethanol production would be higher at 35 degrees Celsius than at 25 degrees Celsius. Also higher at 100% enzyme dose than at 50% enzyme dose. The enzyme dose is just basically what the vendors recommends to put in 1 liter of like 5 liters of slurry, the whole packet. To test this, I prepared a controlled starch rich slurry using foods like bread, rice, pasta, and potatoes. And I used a controlled mixture instead of a mixture household waste, so the substrate would be more reproducible. And I blended all these waste with water to make a uniform slurry. And after like making a uniform slurry, I took a 10 gram of subsample to find out total solids content. And I took that 10 gram of sample and oven dried it at 105 degrees centigrade until the mass was constant. This was needed in order to adjust any water, or you have to reduce any water in the slurry, and we were aiming for 12 to 15% of total solids content in our slurry. Then the slurry was divided into three main enzyme groups: 100% enzymes, 50% enzymes, and no enzymes. And it was heated to 85 degrees Celsius for 60 minutes. And during that stage, I added alpha amylase. And after cooling to 55 to 60 degrees Celsius, I added glucoamylase. And once the slurry cooled below 35 degrees Celsius, I added distiller yeast. And I tested total of 8 treatment groups including 4 main groups and 4 controls. And each treatment was done in triplicate, so there were 3 replicates per condition. And the 4 main groups were room temperature at 100% enzyme plus yeast, room temperature at 50% enzyme plus yeast. 50% is basically the 50% is what the vendor recommends us to use, and 35 at 100% enzyme plus yeast, 35 at 50% enzyme plus yeast. I also included a no enzyme control and a no yeast control, and samples were collected on day 0, day 2, day 5, and day 7, and they were centrifuged and filtered, and they were stored until it was ready to analyze. The ethanol was analyzed by headspace solid phase microextraction gas chromatography, and a 100 micrometer PDMS fiber was exposed into the headspace of the vial for 5 minutes at 55 degrees Celsius. And ethanol concentration was estimated using the ethanol curve, and additional And additional recovery test was also performed on the four main treatments to compare the recovered distillate volume. For the results, the ethanol concentration increased in all four of the main enzyme treaties fermenters, and this can be seen in figure 1 where treatment increased from day 0 to day 7, but the strongest increase was at 35 degrees centigrade Celsius, and by day 7 the 35 degrees centigrade or Celsius 100% treatment gave the highest ethanol concentration at 6.02 plus or minus 0.12%, and the next highest was 35 at 50% enzymes, and it gave us 5.31 plus or minus 0.1%, and the next came out 25 degrees Celsius at 100% enzyme at 3.89 plus or minus 0.89%, and finally at the last was 25 degrees Celsius at 50% enzyme at 2.3 plus or minus 0.05%. So overall, both higher temperature and higher enzyme dose improve ethanol production. In figure 2, as you can see the day 7 endpoint data for the main treatment and the controls. The control group stayed much lower than the enzyme treated group, and the no enzyme plus yeast control remained below 0.6% ethanol, and the no yeast control remained close to 0. And that was important because it shows that both enzyme assisted saccharification and the yeast fermentation were necessary for substantial ethanol production. And statistically, the four main treatments showed a significant effects of temperature, enzyme dose, and interaction between them, with P less than 0.0001. And I also carried out a standardized distillate recovery comparison. In figure 3, the same treatment ranking appeared again. The 35 degrees Celsius 100% enzyme produced a highest recovery distillate volume at 10.17 plus or minus 0.35 milliliters, followed by 35 at 50%, followed by 25 100%, and the last was 25 at 50% enzyme. Even though the recovery test was more exploratory, it supported the overall same pattern seen in the GC result. In conclusion, this project showed that a controlled starch-rich food waste slurry could be used to produce measurable amount of bioethanol, and that ethanol production was strongly influenced by both temperature and enzyme dose, and the best performance came out from 35 at 100% treatment. In the bigger picture, this suggests that starch-rich food waste can be treated as a useful resource rather than just a disposable problem. And it also shows that relatively simple process changes like adjusting fermentation temperatures and enzyme loading can make a really big difference in waste to bioethanol conversion. So for future work, this study could be extended by testing a wider range of enzyme doses and comparing this process to true SSF, which is simultaneous starch saccharification and fermentation, and improving ethanol quantification with more validated recovery method. It would also be useful to test out more variable of food waste mixtures to test whether the same trends hold in less controlled substrate. And finally, I would like to sincerely thank Marla McKenzie and Crystal McFadden for their guidance and encouragement and support throughout their project. And yeah, thank you very much.